Okay, so this is gonna be kind of a switch. Did you guys all read the Reddit thread that I posted?
Yeah, I
Yeah.
skimmed through it.
Okay, so I'm doing basically a major switch from what I initially thought this course was gonna be. Mainly because, and this is also the main reason why I wasn't sticking to like the once a week classes as I was planning to, is because after I talked to all you guys, I'm like, everyone's at a very different level, skill level and everything. And it just didn't make sense to just do lecture style videos. Um, so instead, what I'm going to do is I'm still going to do videos probably every week, if not worst case like every other week. But it's going to be like shorter. It's going to be about half an hour, and it's going to go over like the major questions I get from working with you guys, like one-on-one or the week preceding it. And so that's like the second part of it is I'm just gonna open up my calendar and do like a 30 minutes to 1 hour meeting every week. Um, Probably on the weekends, that's when I have the most time. But every week, and then just after that, we'll correspond over either email or Discord or Reddit, whatever. I'll send you, each one of you, a different like problem based on how well we do on the problem or task I sent you before. So like if I send you a dynamic programming question and you like blow it out of the water, then I'll send something completely different. And then just kind of go from there, and I'll keep track of your guys' progress. So I'm thinking that this should help a lot more than the old style. Okay, so getting started, dynamic programming. I'm not gonna go into the basics here. I'm not gonna really go into code as much. Again, trying to keep this as compressed as possible. I'm just gonna kind of overview it, go over one of the problems, one of the major problems that's thrown on a lot in dynamic programming, and just kind of how to approach it, what's kind of going through my mind while looking at it, and just how to make it easier. And then if you guys haven't filled out that poll yet, please do. That'll give me an idea of where you're at in dynamic programming, so I can send you. I can have a better idea of what kind of problems to send you. So, yeah, dynamic programming, they do seem like the hardest problems right now, but once they click, once you have the ahas, they are one of the easiest. They have a very inbuilt, very structured way to solve and optimize. You start out with brute force. You go from there usually to like top-down recursive, then you add a memoization, then it might bring up, oh, anything better, or can you do bottom up? You do bottom up, and then there's usually an extra step at bottom up where you can improve the space-time complexity even more, and that's the other aha. So like pretty much the same. For instance, so for bottom up, the last aha moment is, hey, I only need to go some finite number of steps backwards to figure out the optimal solution. I don't need all n steps. I don't need to go through every single thing within the array or whatever's been given to me for the problem. Before I go on, is there any questions or anything over what I said? Oh, and also like the new method, the new way I'm going to do this. Any comments or questions?
Sounds good to me. Just in general about dynamic programming, like I looked it up on Geeks for Geeks because I don't have a background with this. It kind of sounded like a way of caching with recursive functions. Is that accurate or not?
Yeah, that's basically it. It's basically about taking subproblems and caching it. They call it memoization. That's basically the same as caching.
Okay.
So if you have subproblems and you have repeated subproblems, essentially, then you can use dynamic programming to solve it.
Sweet.
Yeah. Okay, so yeah, I guess it gets harder because dynamic programming can be applied to a lot of the other, it can be kind of combined with the other topics within this whole like ball of coding interview topics and concepts and everything. So for instance, like tree traversal, bit operation, directed acyclic graphs. But don't worry about that right now. I'm just mentioning it right now. I'm just mentioning it so it doesn't seem so new when you do learn about it later. And yeah, I already remind you guys about the poll. If you're yawning right now, if it's like super easy what I'm talking about, you know, you've done dynamic programming, tree traversal, bit operations, graphs, everything, then you're a much different level than someone who's a little bit confused right now. So I just need to get an idea of that. In the previous class, we had this whole slide. So I'm kind of gonna, I'm gonna kind of show a practical example of this going through the example I'll go over later. What was I saying here? Yeah, I'm just gonna show one example without the code, and just kind of show the dynamic programming template. And then there's one concept I kind of use a lot is like think like a Luddite. You know, without technology, what are you gonna do? Approach every problem as if you're just a layperson. You know nothing about computer science. And for those of you who read Coding the Pragmatic Coding Interview, that's one of the things they really harp on is just you really got to like first look at a problem and figure out how you do it on like pen and paper.
Just a quick question.
Oh, yeah, sure.
Do you still consider that book pretty important right now?
I would say the concepts in it are like everything that they say in it is still relevant. I think a lot of the problems are kind of outdated. Yeah, I mean, it's still a good book to have to like go where everything is talking about, and then I would say for the problems, use that the 75 blind 75 list I gave, and there's one I think I mentioned in the other class. There's another one that's like 175 problems, but it's still a good book. It's still relevant. It's just the problems aren't as relevant anymore.
Okay.
Yeah. Okay, so yeah, again, this is like I realized I forget who was talking before, but I know there's one of you who's probably kind of confused by what iterative versus iterative like iterative bottom-up tabulation versus recursive, which is top-down means, and like how to implement that, how that works with dynamic programming. So I was going to mention this before, but if you are confused, if this is going too fast for you, that's okay. It's completely normal. This is all going to be recorded, so you can go back to this, refer back to it, and like a lot of things I'm saying right now will make more sense later if you don't get it right now. But yeah, as you work through the problems, you can use this lecture kind of as a reference point, and you'll understand things a little bit later. So first of all, the recursive solution is almost always best to discuss and implement first. It's easier to implement first of all, and for the bottom up, you need a little bit more understanding of the exact recurrence relationship to know exactly how to figure that out, how to write the code for that and everything, and how to tabulate it. But you also must know that bottom up, if they bring up the possibility of Stack Overflow with recursive solutions, which can even happen with normalization, the bottom up solution will usually, with one further optimization, have a better space complexity than recursion. And recursion will pretty much always be O of n. I did have a slide in here kind of going over why recursion is, always O of n, like top-down recursion. But I can still kind of go over it if you guys want.
If you don't mind.
Okay, I'll do that later then. I'm gonna switch the iPad soon for the example, and then we'll go over that. All right, so switch the iPad. This is the first problem I'm gonna go over. So, have any of you seen this before?
I have.
Yeah, I've seen it before.
I haven't.
Okay, cool. And you've like, how easy was it for you guys?
It took a little bit of time, but I was able to get it.
Cool. So yeah, I'll go over it just to show like how I look at these problems. So, for those of you who like don't know what this is, you're a professional robber. You're planning to rob houses along the street, and each house has a certain amount of money stashed, and you're able to only rob houses that are one apart from each other. So you want to figure out the maximum amount of money they can rob without alerting the police. So the first thing here is just the first like tip off, like the first 2 seconds. If I see anything like what I call optimal keywords, like maximum or minimum or total amount, I consider those like keywords that like, okay, this might be leaning towards being something that can be solved down in programming, something that has subproblems. Right? So looking at this, hold on, just switch to iPad. All right, cool. All right, so and also if you guys want to follow along, you can look up the house robber problem on LeetCode. It's number 198. So we have 4 houses here. So first of all, we found like it's a maximum amount, and we need to go through these houses that have 1, 2, 3, 1, and we want to find the maximum that you can rob. You can only rob houses that are non-adjacent. So the first thing I look at is like, okay, for getting the maximum amount of money, there's what I need to do here. At each point, I need to figure out, if I start here, I need to either skip it or go to the next one, or take it and go to the next one, and keep doing that at each house until I have, the amount of money within that, like run through of houses to, or like that parallel universe, in a sense of yeah. So sorry, the brute force is I'll just go. I'm gonna go to each house. I'm gonna figure out exactly what amount I'll get from every possible combination of houses that I can go through. So right there, you can see like there's multiple possibilities, right? So that means there's multiple like subproblems. And then on top of that, to determine like dynamic programming, it's kind of harder with just this smaller, like having a little bit of a smaller example. But let's see, if you have 1, 2, 3, 1, you're doing, sorry, the first thing you want to look at is, are there any changing variables? So the changing variables here are the location. Like at every point, you start at 0, then you go to 1 or 2, then you go to 3, or you're stopping entirely there. And the other one is the amount that you've kind of robbed. So it's your profit, current profit, and current location that's changing. Essentially, at each point, is there a problem you're doing, right? Like, let's say you're dropped right here in the middle at 2. You'd have to figure out, you need your current profit, and you need to figure out like what to do next, which is either you add 2 to your knapsack, to your duffel bag of money. So this will be whatever this is. What are you starting with? X plus 2. So that's going to be your current profit is X plus 2, or you skip it and X plus 2, and then your index from there, you're gonna have to skip this and go straight to 3. So that'll be your index will be your current index plus 2, where if you actually skip this, Then your next index is going to be your starting index plus starting index plus 1, and your profit is going to be the same as a starting profit. Let me just make this a little more clear. So your profit is starting profit plus 2, just that's 2 there, and your and your index is starting index plus 2 because you skip the next one. And if you don't, then your profit is starting profit and starting index plus 1. So that kind of skipped around a little bit, but essentially the part about recognizing it just comes down to first thing is like the maximum thing is, does that mean that we need to go through multiple sub problems, right? Do we need to figure out multiple different combinations of going through this this array of houses, array of whatever that comes up? And if so, can we like store some of those solutions to better figure out what to like make this problem a little more optimal? And storing the solution part, that's a little bit harder to explain without going a little bit forward. So I'm going to show you that in a second. But just to get some feedback, is there's this part about like recognizing by looking at the optimal keywords, looking at there being multiple combinations that you need to go through. Does that part make sense?
Yeah, I understand that.
Okay, cool. Okay, so the two things that are most important in, well, the biggest thing about the dynamic programming problem that most people struggle with is figuring out the recurrence relation. Like once you have that down solidly, then the rest of the problem is a lot easier. And to do that, again, you go to each, go to a number in the array and you figure out what operations are available at that point, right? What problems are you doing at that point? Which is what we just did, right? You have two options at any house. Let's say you're just like an outsider and you come in later, and the robber, you're seeing a kind of, parallel universe where the robber skipped this one, went straight to this. So what do you have to figure out, right? What you have to figure out is where to go next, and the two options you have available are saving it or skipping it. And that's always what you need to know, just to figure out the brute force solution. The first thing you should be doing. So basically all dynamic programming questions, you can start out just by knowing that it's going to be O of x to the n, where x is the amount of operations available at a point in within your array or what are you going through. So this is going to be O of 2 to the n, and then the recurrence, what do you call it? The recursion space-time complexity is going to be O of n. And so you guys asked about that earlier too. I'm going to really quick go over why the recurrence relation or the recurrent space complexity is O of n. So it's 1, 2, 3, 1. So let's say we start at 1. We have two options. Basically, it splits off into two little parallel universes where we can either save it, add this to our loot, or skip it. So we always start, we start with 0 in our duffel bag. So now if you save it, we have 1, and if you skip it, we have 0. And then if where are we at? So if you saved it, then we would be this would be the current current profit, and then from there we would have to go to the index of, we'd have to go to 3. We have to skip 2 because we can't rob adjacent. So it'd be I equals 2. So you go from there, I equals 2, and then the profit at that point would be 3. And then over here, if you went and you skipped it, then you would go straight to the next one to do the same 2 operations again, and you do I equals, after that you go to I equals, that would be I equals 1 and P equals 2. So essentially you keep doing that. And the way that you would write the code is you would do basically, if you, first one would be save, first iterate, and then save save the current profit, and you would call this function, whatever it is. I usually write in Ruby, so let's just call this, I don't know, robber. And this would always take in the array and the index and profit. Right, and then you would do, if you save the current thing, then you would do, you would call that recurrence relation again with the same array, but the index would change to index. That's what we did here, index plus 2, because we were skipping that one, and then profit, you've increased that by whatever it was at that point, which is array index. I mean, this part, for what I'm saying, it doesn't matter as much, but I'm not gonna write the rest of it out. So this one will be robber, the same thing, except it would be index plus 1, and then just profit, because you're not adding anything at that point. When you go to the recurrence relationship and you hit robber, that first one, then that part has to resolve before it goes to this one. So basically, if you look at it within this tree, then you're starting out here with index of 0. This whole function, the first one starts out with index of 0, and then you go to the save one first, because that's written first in the code. So you go here, and then that recalls this robber thing with the different index and profit, and it goes to the next one. Again, it will go through to this part again, so it'll go to the save one again. So this will be, it went from 1 to 3, so now you're at current profit, you're adding 3, so you're at 4. And I mean, that's pretty much the end of it. You can't really, you have to skip the next one, and that's the end of that array. So now, once this part is done, that current profit, because you have, you're gonna have base cases here, so you're gonna have a base case here of when the index is, either more than the length of the array, or if, actually, it would just be if index is index more than length of the array, then we just return the profit. It's not writing that well. So you go through this, like you go through that whole thing, that whole stack, and then you return it. So then the stack is like cleared. You return one number at that point, 4 in this case, and then after that you're like at this point, and then you can go to the next thing, which is skipping it within that kind of nested parallel universes you've gone into. So now you're here, you've skipped it. So you go here, and then again you go through the same thing again. So like you go through, you go through this whole part, and then once that's returned, then you start the next one. So it's like it's a little bit like depth first search, if you guys have done that. But essentially, you have to finish your first. You have to go all the way down to the very end of adding to your recursive stack over and over. And then once that returns, only then can you go into your next stack. So that's why the space time for recursion is O of n. And I mean, this can change with different problems. Like, I'm not going to go into those ones, but essentially it's going to be O of n with recursion with this kind of two changing variables kind of problem. Any questions on that?
No.
Does it like make sense, or is it a little bit confusing? So
I think it makes sense.
I understand it.
all right, cool. Where was I? Yeah, so the recurrence relationship either here is like at each point your chaining variables is your profit and your index. Profit, index, and at each point in this array, you're just figuring out. So you're either doing profit plus, or let's say current profit plus the array of profits index, and then after that you have to skip the next one. God damn it. Index plus 2. So this is, one of your recurrence relationships. That's one of the possibilities. And the other possibility is you keep the current profit, you don't add wherever you're at, and then you go straight to the next house. There's only two things to do at each one, and that's why it's O of 2 of n for brute force. I'm just gonna go like really quick over the top down, the memoization. Essentially, what you're gonna do is this is another big part of it is the array size. So with dynamic programming problems, you'll always only have 1D or 2D arrays, which is two changing variables is a 1D array, and three changing variables, which I'm not going to go over today. That'll be a 2D array. But right now, I'm just going to show you the 1D array. Now, you could go more. You could have 4 or 5 chaining variables, but you're never going to see that in an interview because it will take way too long to like process and do an interview. So you don't have to worry about that. These are the only two you have to worry about. Okay, so the 1D array here is with the two chaining variables. Basically, you have an array, and the index of the array is your location in the array, and then this will equal your profit, your current profit. So essentially, you have 1, 2, 3, 1, 1, 2, 3, 1. And at each point, you're figuring out the profit. So you're saying, okay, for 1D array, you have what's your maximum profit if it was literally just one house with 1. Easy, right? That's just 1. Now, what if it was 2 houses? We have just this part, 1, 2. Then you have 2 choices, right? You can either save or skip this and get the 2, or you can save this, get the 1. So obviously 2 is better. You're better off skipping 1 and getting 2. So now your maximum profit is 2. Then you go to even further, 1, 2, 3. Now what's your best option? You can either do one, you can save one or steal from one, and or the first one, and then you skip to 3, so that's 4. Or you can skip this, take from 2, and then you get just 2. So obviously 4 is better. I mean, the other possible combination is you skip 1 and 2 and you go straight to 3, but obviously that doesn't make sense either. And that's actually one of the aha moments. Why would he skip both of these and go to this? You know, why not at least take this in this particular case? You'll see that matters later. So, okay, 4 is the one for here. And then you do 1, 1, 2, 3, 1. And then now you have, you know, even more options. So you have 1, and then you can go to 3. So that's 4 again. You can skip this, get 2, and then go to 1. That's 3. And that's pretty much it, right? Unless you want to do something kind of stupid here, which is skip both of these and do 3, or skip all 3 and do 1. Doesn't make sense. So your profit is still 4. And this is basically, you know, what you'll end up doing for like the bottom-up tabulation approach. I'm going to kind of skip that today as well. But this is the most important, this part, the chaining variables, your location and your profit, and the recurrence relationships at each point. So this is like basically what you're going to code. This is at each point you're going to recursively call the recurrence relationship again and do this and then do this. And then to memoize, to cache it, you would use this kind of 1D array, and you would say, okay, so when you get back when the recurrence, the stack returns whatever this is, you save that as you know, dp of I. And then for each time you go through this, you can figure out what is the have you already gone over that problem before? Okay, so I know that was pretty fast go through. I didn't really fully get to go through, you know, top down, bottom up, but I do want to finish the rest of the presentation. And again, I'm gonna give you guys like easy or hard problems based on where you guys feel you are, and then as needed, I can teach you the rest of it. Those of you who've already seen this problem, who understand everything I was doing, if you're already advanced with it, one thing that really helps with understanding new concepts is kind of playing with the problem and turning it and kind of adding in that concept. So playing with the problem that you're already familiar with. And example I like to give, most of you, have you guys heard of the two-sum problem? This is what it looks like. Input is an array of numbers, and you have a target number. And then you have to figure out whether 2 numbers within that array equal the target number. Have you guys heard of that problem?
Yeah, usually you'd solve it with a hash table or something.
Yeah, exactly. So that's a pretty, you know, fairly simple problem. Now, if you're familiar with it and you're you already kind of get down in programming, what I want you to do is just go and turn that problem into a dynamic programming problem. So, and then try to solve it. So for instance, you know, what if there could be multiple pairs of numbers in that array that equal the target number? And out of those multiple pairs, what if you had to find I put insert optimal wording here. So basically, what if you had to find the maximum difference between those pairs of numbers, or anything like that. But that's one thing you can try. And then another advanced kind of thing is to look at whether or not you could solve your new problem with the greedy approach. Why or why not? That one, you know, you can definitely skip that part.